Fernando, how's it going, mate?
Good. How are you?
Good, man. Good. No, recently, you had one of your blog posts hit Hacker News, which was the developing lessons learned on how to develop a compiler
Yes.
for your programming language, Austral. And I thought it would be great. I thoroughly enjoy your writing. I thought, geez, let me reach out to you and see if I can hear your side of the story. I want to hear what's the background with Austral, with all your the enlightened writing that you got. I think this might be an interesting conversation. So, hello, welcome.
Thank you. Thanks for having me. And thanks for your kind comments. It's I tried to put some effort into the prose, but I can't guarantee the quality. Do you want me to just jump into the introduction of the language?
Yeah.
Okay. So Austral is a new programming language. It's a generally like low-level language. You can think of it basically as either Rust, the good parts, or a more modern take on Ada or Pascal or something along those lines. The design goals for the language are basically just simplicity. So the language is designed to be simple enough that you can just fit it in your head. There's no need for language lawyering. It's not like C++ where you could spend a lifetime writing C++ and there's still some dark corner that you've yet to explore. Strictness along the lines of Haskell and such. There's 1,000 little liberties that our language take, where this is in Austral it's much more locked down. And the design goals generally stem from a different view of programming, where it's like programming languages generally are some people phrase this as an issue of trust, where it's framed as, some programming languages like C trust the programmer to get it right. And some programming languages like Haskell or Rust distrust the programmer and put all these boundaries and limitations. But I try, yes, the guardrails that many programmers were sent. But I think of it as a matter of how much you're burdened by programming. I like to make this analogy to aviation, where, if we flew planes the way we write code, we would have daily plane crashes. And the comments from all the armchair pilots would be like, well, it's their fault because they didn't read, subsection 7.2.1.1, where the manual says that, at 3 p.m.
Well, there you go. You see a good example.
At 3 p.m. on a Tuesday, the wings fall off the plane, and that's expected behavior. And why didn't you know that? Yeah. Of course, in aviation, we didn't do that because we accepted that human error is just an inseparable and intrinsic part of human activity.
Yeah.
People are tired and they're burned out and they're traumatized by writing executable YAML, and they have a limited working memory, limited attention span. They have constant business pressures to release. So it's not really about, often when there's a massive security vulnerability, the argument is made that this is somehow like a comment on the programmer's virtue, that if they were a better programmer, they just wouldn't have bugs. But the long train of hilarious and astounding security vulnerabilities kind of proves that, this isn't the case. People are doing their best and they keep failing because their tools are insufficient. And, go ahead.
Yeah, no, I completely agree with you. I remember one guy telling me, like, why can't we build software the way we build bridges, And, I've spent a long time sort of thinking about that. And I don't know, it seems like the mythical sort of thing that one can actually achieve. But in the recent podcast I had with I forgot his name. We were talking about joint calculus, and
yes,
he's written a book on the science of functional programming, basically, where he sort of like breaks apart some sort of like almost axioms of a programming language that sort of like lead or guide, just like mathematics or some other like constructs within engineering would lead or guide the engineer to creating better products. Like, for example, I mean, you can create buildings that fall down, like in China. That does happen. But you know, like generally speaking, you've got the tools which are able to sort of lead or guide you in the right direction and don't fight you. And at least in my opinion, like a lot of functional programming has, well, not a lot, but some of the core bits of functional programming actually do lead or guide you in a intuitive way. Now, I'm interested. Like you chose to go for a very low level sort of procedural programming language. What was the reason for going that direction?
Well, it's because of this design goal of simplicity. Like Austral doesn't have a garbage collector, for example, and it's not because of performance. Because that's a common argument that people make about against garbage collection. Arguably, performance predictability would be a better argument. The reason it doesn't have a garbage collector is that it's simply too much complexity. You need a fat runtime. Garbage collection algorithms are very subtle. You need to handle concurrency. You need to handle performance, and you have this natural trajectory that every JVM goes through, where it's like you add more and more parameters to tune the garbage collector. And I think it was the creator of the Go programming language that said you eventually have someone who's the full-time garbage collector tuner. And yeah, you need like, and Go, you know, calling C code from Go is very complicated because it has this complicated fat runtime, and it has user space threads, and you need some sort of weird synchronization that I don't understand. So the reason it's very Spartan is because I don't want to have to deal with all these complicated things. And a low-level language just means there's less to understand as a whole.
Okay. And then what attracted me so much towards your writings, as well as you the way you communicated along with the implementation, is that you've found a lovely little combination of linear types, error handling, and then you know, what was it,
capability, basically.
Yes, capabilities, the security side of things, and the way those sort of like tie in together is actually quite beautiful. When I saw that, then I thought, God damn it! Okay, now I want to hear the story surrounding this particular design decision, how you arrived at that. Yeah, and maybe later we can also open up, like, for example, the comparison with affine types of Rust. And, you know, this sort of chapter, we might be interesting to go into that, if you don't mind.
Right. Well, the design, I've done my best. I can at least say that if it is not perfect, and it does have a couple of rough corners, it is at least internally consistent and coherent.
Yes. That's admirable, I tell you.
Thank you. Yeah, it wasn't designed in 2 weeks like JavaScript, which is not actually a comment against JavaScript. It's actually a comment against me. I spent a very long time on the design, like truly an embarrassing amount of time, to the point where I was ashamed to talk about it with my friends, because it was, it's that language that you've been writing since, more or less, yes. Since like 2016. So I was ashamed to talk with my friends because it was, it was like, it's the programming language that you're going to finish someday. It evolved a lot. The design changed a lot. I had to explore like a big section of the programming language design space, but eventually it sort of fell into place. You know, actually the first thing I wanted to make a very long time ago was like a statically typed version of Common Lisp, which is kind of a tall order, because Common Lisp has a bunch of it's very, very idiosyncratic and strange, and you can't really modify it. Although a friend from Twitter has actually just done that, and it's called Colton, like Cole, TON, and it's statically typed, sort of Haskell on top of Common Lisp. But yeah, that required a great deal of thinking, and I eventually started to just began zeroing in on the present design. It's informed by like Rust. It's informed by like older languages didn't quite make it to production, like Cyclone. That was an old research programming language. There's a bunch of programming languages. Yes, that's mentioned. Things that exist only in citations. Paclang is a great example because it's like it exists vaguely in like a PDF that you can find maybe, and it's ethereal and mysterious, and you can't really find any references to it. There's a language from Microsoft Research called Bolt. They do a lot of great work. So yeah, that was part of like how I developed the system. And I wish I had actually kept like lab notes and a bibliography, because I can't really quite trace the genealogy of ideas linked to the language. But yeah, the basic point is, yeah, I came into a thing that I sort of follow the ideas quite naturally, and they led to something that I'm fairly happy with, and it satisfies all the requirements that I have in my head for like a programming language, which is like it should be roughly orthogonal. Features should not impinge upon one another, which is very hard to do in programming languages, because the natural tendency is for everything to bump into each other and intersect in nasty ways, creating all sorts of complexity. It's simple enough that you can just read the spec from beginning to end, which is currently like 110 pages, and most of that is the rationale, which just explains the various features and why this, why not this, what was left in the cutting room floor. Yeah, the actual spec is very short. And yeah, the goal is to make a tiny language that fits in your head and evolves slowly, and that you can write code and have it compile and have a good amount of confidence that it's going to work, and leave that alone for 30 years and come back later and just compile it again and run it again.
And that's how you get your bridges.
Yeah. That's a good analogy. Why software is so unreliable is a difficult question that I can't really answer. I think, programmers are often very reactionary in terms of like rejecting theory, like ideas from theory. I know I was more of a practical minded. I don't need computer science stuff, but and Austral is not like an ivory tower fanciful language. There's a quote that I like from this computer security paper that's like, the ship carries stones from the ivory tower, but only as ballast. I'm paraphrasing a bit.
Yeah, right.
Yeah. So it might be a hard sell to talk about like, linear types and type universes and things like that, and convince people that no, this isn't an ivory tower thing. This is actually quite ordinary and workmanlike, but I'll try.
Yeah, no, I've gone through a similar sort of learning curve, beginning like starting off with like, no, these academics are too airy fairy. And then kind of start to see as time goes by, you're like, actually the academics were right. At least over here. Sure, the grad students come along and fuck up things, make the most awful of implementations that are completely and utterly unusable. But then you're like, okay, let's pick out the gems in the papers and then compose it into this nice little thing. And then after about 25 years, it becomes mainstream, and people are just like, yes, this is normal. And I think it's about a time that I think what with Rust have sort of introduced, loosely speaking, linear types or affine types into the sort of the programmer's lexicon. Now we're in a situation where people are starting to realize that this is actually a pretty good direction. So maybe you want to tell us exactly what is linear types, and why didn't you go with, for example, affine types, or even the difference between the two, etc.
Good. Yes. I've actually prepared the slides for this, so maybe I'll check this.
Dude, can you? Yeah, this is great. You've done that. Do we need to do something?
Hold on.
Share screen.
Why isn't this working?
No. Just wait. Okay, multiple participants can share simultaneously. Dual monitors. Okay, who can share? All participants. Who can start sharing when someone else is sharing? Oh, Jesus, just Okay, now try share now. Aha.
Does this work?
I see something.
See.
Yes.
Good. Let's see.
Ooh, this is the first time there's a
Blah blah blah.
slideshow.
Motivation.
Awesome,
blah.
brother.
Oh yes.
Dude, you got 50 slides there.
It's just a. I wonder
Okay,
if
no
this is a
problem.
shortcut. Okay, whatever. Next page. Right. So, what's the
How's your-
motivation?
can you sort your microphone? Your microphone a little bit closer. Just now it was
Good.
Yeah, that's good. Okay, shoot,
Good.
mate.
Okay, linear types. Why do we want linear types? So there's basically, if you look at any graph of security vulnerabilities in like C or C++ programs, it's all like memory buffer overflows, things like that. Some programming languages solve that by putting a garbage collector and not letting you touch memory at the cost of introducing a lot of complexity and performance issues, and having to tune the JVM's garbage collector for all eternity, which is a Sisyphean task. And so linear types, they provide three features. They allow you to enforce high-level protocols in software. They allow you to prevent a huge class of security vulnerabilities, and they allow you to constrain, like types do, like a good type system does. It allows you to sort of add semantics, to add meaning to your program, and constrain the space of possible programs. Right. And the motivation I chose here is just a file system API with like C syntax, where you have just the file type. You have open file, takes a string and opens file. Right. Write the string to a file, close the file. Right. Implicitly, programmers know what this does. There's an implicit life cycle to the file object, right, where it's this: you create the file, you write 0 or more times, and then you close it. But the programming languages don't really allow you to enforce this. So you can represent the life cycle as like a graph, where you start with open file and then you can close it, or you can write to a string to it n times and then close the file. But you cannot actually enforce this. And in fact, if you add all the other transitions that the programming language permits you to do, you have all these erroneous transitions where you can open a file and forget and just do nothing and leak memory. Or you can write to a string and then also forget to close the file and leak memory. You can close the file twice. You can try to use the file after it's been closed. And in a file system API, it doesn't much matter. But with this also applies to pointers, where allocating memory, the referencing and writing to pointers, and freeing pointers is the equivalent of these instructions. And when you leak memory, it's a more significant problem. And not freeing memory twice or using memory after it has been freed, it's the thread that you pull on that collapses the whole thing, because you got all these security vulnerabilities with buffer overflows. You can access secure data that has been properly wiped. And right, so they basically fall into two categories: leaks and using something basically in the wrong order. Yeah. And this applies to everything that's a resource, any value that has a life cycle, like sockets, like pointers, to memory, like file handles, like database handles, anything that has this sort of protocol that has to be followed. And the standard solution is to throw static analysis at it. And static analysis is you have a bunch of programs that scan the source code and look for these type of vulnerabilities. And as with all things, it's like an 80-20 thing, where they can find the 80% of the most common zero-day vulnerabilities, but the more subtle things that happen because there's there's greater indirection, those things are harder to spot.
Can I would like to interrupt a little bit and ask a question. In the implementation, when you have I imagine at some point there should be a pass on the compiler when you're compiling this, and you've done all your types, type checking and whatnot. You would need to do a linear type check pass.
Yes.
And at that point, you are essentially doing what the static analysis tool would do.
Well, yeah.
So does that not apply?
There's a subtle difference because of soundness. Linear types, so like a type system, the thing about a type system is that it can have false positives. It can flag as incorrect a program that might actually run if it was a dynamically typed language. But they don't have false negatives. At least a sound type system should not have false negatives. It should not accept a program that has a type error and would crash at runtime. It should not accept it as valid. Static analysis is the opposite, where it's kind of like unit testing, where it can prove the presence of bugs, but it cannot show their absence. And the problem is really quite fundamental, because language semantics, you can't really work around them. Like if the language permits all these liberties that lead to security vulnerabilities, you can try to constrain that after the fact, and you can do a static analysis, but it's not really possible to like slap a type system on a programming language after the fact and expect things to work with minimal intervention or no intervention at all. So the problem
it's I suppose it's like holding a cup of water, like water in your hands, and it just leaks through your hands, your fingers.
Yeah, it's just that, you know, the foundations matter and you just can't get around it.
Yeah.
And that's why you couldn't write like a Rust analyzer for C, and Rust had to be invented. It's because you can just pile heuristic upon heuristic upon heuristic. There's always going to be something that slips out because you have all these huge code bases. Linux is the classic code base that every static analysis tool is trained on. Yes. Linux still has security vulnerabilities, even after all these interventions, because fundamentally it's written in C and there's serious problems that can't be corrected after the fact. But yeah, so the problem with the static analysis is that it just doesn't catch every case. And what you want is a solution that's simple enough that it doesn't just burden you horribly when you're writing the code. So like theorem proving and, you know, code verification are kind of ruled out by this, because even if they can be made simple, they do involve quite a great deal of unseen infrastructure, like automated theorem prover software or SMT solvers are just huge code bases that are almost impossible to certify the correctness of them. Yeah, so it has to be simple. It has to catch every case. And ideally, it should be just a fixed set of rules that you learn once and you apply them everywhere, rather than just an ever-changing pile of special cases and rules and heuristics that just grows forever to try to encompass. Right. So it's not about, you know, adding to the type system to catch errors. It's about removing possibilities for error until you have something that's simple,
right,
from which errors cannot spring. And the solution is to all this is linear types. Just as a type basically represents a set of values, which is not uncontroversial. But a type is a set of values that share some structure or behavior. And linear types are types whose values can only be used once. And I think of an example, right? And the way Austral does this is very simple. This set of types is divided into two universes. There's the free or unrestricted universe that contains types that are not linear, which can be copied harmlessly. Essentially anything that's not a resource. Integers, floats, aggregate types containing other free values, you know, like string constants. And then there's a linear
types, right?
Or just like the primitives, just things that can be copied that are not like pointing to memory, that don't have a life cycle associated to them. Okay. Then there's a linear types, which are essentially everything that has a life cycle or a protocol that has to be followed. Yeah, and types can only become linear by either declaring them linear. For example, you know, you may want, here's a record that has field X, that's an integer, Y, that's another integer. These are both free types, but you can declare that it's linear to make the thing linear, because you may want to treat it as linear for whatever reason. So you don't forget to use it, for example. And also by containment, because linear types are viral. You can, if T is a linear type and you put it in a record, this whole thing is linear.
So it's it's the GPL of type systems.
Yes, correct. It's just as a GPL is viral, linear types, you cannot hide them in a free type.
Okay.
And
so then that means the very top level. Oh, yeah, okay, yeah. The very top level of that thing would be a linear type.
Correct.
All the way through, yeah. Okay.
It always just one drop rule.
Yeah.
And the second rule is that, types, value of a linear type has to be used exactly once, not 0 times and not n times, just once. And this doesn't require runtime checking to enforce. It requires just a very simple compile time check.
Okay.
And the code that does is actually quite simple. It is 600 lines of code. So
nice.
Thank you. It's mostly because it's doing less, because it's designed to be a simple system.
Yes.
Essentially, it means that a variable of a linear type can only appear once, with some subtleties. For example, if f is a function that returns a linear type L, this doesn't work because you're defining the variable and then you're discarding it silently, and you're using it 0 times.
That's a no-go. Yeah.
That's no. This won't pass because X is being defined and then you're using it twice.
Yeah.
This will pass because X is being defined here and
then
it's
you
being
consume
used
it
here. Yes.
Right.
And this is called using a variable is called consuming it. Beyond this point, it is not usable.
Okay.
There's a couple of subtleties. For example,
that shouldn't fly. That shouldn't work.
Because it's not quite that it only appears once in the source code. For example, if it appears once, it has to appear consistently in if statement branches.
Okay, so both the branches must get it, must see it.
Okay. Either it doesn't appear in both branches or it appears in both, but not one or the other, because at this point, after the if statement, the compiler doesn't know where it's consumed or not.
It makes sense, yeah.
So this passes because you're using the variable x once in both branches. And just the final subtlety is just like loops. If you define it outside the loop, you cannot use it inside the loop because quite simply it could be used any number of times.
Okay, I have a question on this one.
Yes.
So as I emailed you, I'm also implementing a programming language, and this is one of the primary reasons why I'm thoroughly interested in your work. Except I don't have loop constructs. I want to purely deal with recursion. So old school Erlang style, there's no loops, there's no for loops, none of that. Just do recursion with some guards, and you can like exit the recursive loop depending on certain conditions. Now, the thing that I've arrived at, the equivalent sort of rule in your situation, you say you can only okay, what's your rule here is that you can only have once per iteration, right?
You can move the variable into the loop, but you can't use a variable defined outside the loop inside that loop.
So this means as a recursive function, you should not be able to pass in a linear type as in the function signature. Is that correct?
I think you can. It might be good to look at an example, but the basic idea is that you suppose you have an if statement or if expression, if you want to have an expression-based language.
Yes, it would be.
Basically, in the branch that's for the base case of the recursion, you consume the value, and in the branch that's for the recursive case, you just pass it to the function again. So you're using it in both branches.
Hang about. Look, okay, let's not add a conditional. We just do a recursion. And then what will happen is that you keep passing that recursion, that linear type, into the function, each time.
If you have an infinite loop, that is unsound. But that is the case with
sorry, of course you have to have a conditional because you want to exit the freaking thing.
I mean, this is the case. This is kind of an asterisk. This is the case for every Turing complete programming language. The type system is unsound. If you have a function that's like f that returns a type t, and then the body of that function is just return f parentheses, so that it recurses forever. The type system is actually unsound because this function doesn't actually return t; it just recurses forever. So it's kind of a lie. So in a sense, every type system that allows you to have like infinite recursion is unsound. But I mean this may sound self-serving, but I think that's a rather minor detail.
Yes, you're right. It's kind of like a divide by zero, maybe sort of kind of thing.
I mean, like you can just when there are infinite loops, a lot of guarantees just don't apply for type systems in general.
Okay. So then, okay, just to repeat what you said earlier on in the conditional. No, actually, could you repeat what you said earlier on about the conditional?
So basically, every recursive function, you're going to have some sort of conditional expression where you have the base case where you just end the recursion.
Yes.
And the recursive case where you just keep iterating, and you simply ensure to consume the argument in both.
Okay.
I'm just trying to think of an example. But there's not necessarily very simple examples. But if you imagine maybe a recursive factorial function, just pretend that the argument is linear and that is consumed by comparing it to 0. And then if it is 0, you return 1. And if it isn't, you just continue the recursion.
You don't actually.
This is a good example because you can't consume it because you have to take a copy of it for the n-1 case, right? This isn't a great example, but I mean, you can write recursive functions in Austral. It's just I don't have a good example of that at the moment. Besides, I haven't introduced this, but you can use borrowing, which allows you to treat linear types as locally free, so to speak, and that lets you escape a lot of the guarantees. But yeah, like after this, I'll probably just write up a quick example of the recursive function in Austral using linear types and show that it can be done. But you can certainly do it. I mean, it doesn't.
That would be great.
A lot of the restrictions on linear types are somewhat onerous, but they don't really prevent you from writing code that you. They really only prevent you from writing code that will be incorrect.
I'm happy about those trade-offs, mate. I'm happy about those trade-offs. Like I don't want. I hate things going bump in the night. And
right.
If you and just as you go through a learning curve with Rust, you know, the borrow checker smacks you on the wrist, smacks you on the knuckles, and eventually you start to learn, and then you start to write decent code, and that actually works. So I mean, yeah. So anyway, I'd love to see that example of a recursive function using linear types in Austral. That would be really excellent to see.
Yeah.
And then maybe I don't know if you would add some sort of a rule. Probably not.
No.
Variation.
I'm quite sure it's the type system is complete as it is. It's just that I haven't had many. I think the README has an example of a recursive function, but it's not using linear types. It's just that a lot of cases where you would use recursion, and borrowing just obviates a lot of those difficulties.
Okay.
But to your point about things going bump in the night, yeah, I think when I was younger, I was much more interested in having expressive power, and I liked Common Lisp because that was the first programming language that I felt really productive in. And I have a draft of a blog post that I have to finish about this because Common Lisp is a really great language at making you feel like a wizard.
Yes,
like you're casting spells, and that's all well and good. But after quite some time, I think close to 10 years now in this industry, the last thing I want is power. I just want fewer nightmares. You know, I want fewer just because all these languages that are so dynamic and so wonderful and so productive, within a year, the code base is just a mental health hustle. You know, it's just lock it down enough already with the macros and the reflection and the dynamism and the everything's reflective. No, let's just do something simple that works.
I agree with you completely, mate. I agree with you completely.
I mean, you have to have burned out 68 times to appreciate this language. Otherwise, it just feels like there's too much strictness.
Yeah.
Continuing this, it's just
please go. Let's go for it. Yeah.
This is fine because you're moving the variable into the loop. Blah blah blah. Oh, and this is just an example of like how will you do a linear file system API?
Right.
This is just Austral syntax. There's a file type which is linear. A function open file, essentially the same as the previous example. Takes a string, returns a file. Write string, takes a file, a string, and returns a file. Close file, returns a file. So does this. Can we actually leak a file? like we saw earlier. Well, no, because if you do this, if you open the file and just leave it dangling,
that
it
won't
will fail
yeah.
because it's never consumed.
Okay.
Similarly, you cannot write this because write string returns a linear file object, and you cannot silently discard a linear value. So that doesn't pass. So if you look at this, the graph with the mistaken transactions, these leaks, we can take them out. And we're left with just these two errors. The use of the close and double close. We can't close a file twice because the file is consumed here. And at this point, it has already been consumed. The compiler will raise an error.
So remove that after
remove
use.
the double close. And use after close, similarly, consumed here, used again here, compiler detects it. Very trivial, just rejected. And now we're back where we started, where we have the precise protocol that we had in our heads and that we wanted to implement. And now the language allows us to implement it actually strictly. And yeah, the type system essentially forces you to the correct usage, which is you open the file, you write n times. Each time you consume the variable and assign to a new one.
Yes.
And close the file. And yeah, it matches all the requirements we want. Is it simple? Yeah, you can write down all the rules and just put your hand over them because they fit on a page. And in fact, I have somewhere in the specification this linearity checking, blah blah blah. Here it is. Yeah, like you can just.
Oh, where was it? Oh, there you go. Oh, yeah. That's lovely.
Oh, that's all there is to it. And this includes borrowing and the convenience ergonomic features, and that's all there is to it. And this is more a specification rather than an interactive material. So I don't want to like necessarily go through it. This is just like introduction. Is it correct? Yes, because it satisfies all of the things we want, and it's static because it's just a fixed set of rules, rather than some endlessly growing pile of rules and detectors and special cases for the various things. And as a more sophisticated example, you have like a database API where you have a linear database type. I forgot to put the linear type. Linear transaction type. You open a database. Oh, this should. Oh God! Now I have all the problems. Yeah.
Okay, so this should also be.
Yeah, this should take a database argument.
Yes.
Start consumes the database and gives you a transaction. Query takes a transaction and a string and gives you a transaction. Commit and cancel give you close the transaction by either executing it or canceling it and give you back the database.
Okay, just to press pause. This module DB is the module header. Is that correct?
Yes. Okay. Yes. So Austral has probably a somewhat controversial feature. It separates module interfaces from module implementations. And to be clear, this isn't like in C or C++ where it's like a kind of a hack to enable compiling.
That's the first thing that crossed my mind. I was dude, this is not the 80s, the 70s. What the hell?
No, it's not a hack for separate compilation. I know this was going to be a controversial feature. The language will work just the same if modules were defined in a single file and you had like public, private, opaque modifiers. In fact, there is a step in the compiler that takes the header file and the interface file and the body file and merges them into a single object.
Yeah.
No, but the reason this is because I used standard ML and later OCaml, and it's actually quite wonderful to have the interfaces separated from the modules because you can put all the documentation in the interface and separate interface documentation from implementation documentation, and just have like when you're checking code, when you're trying to like remember, bring back into your working memory what's the interface of a module, you don't have to scroll through hundreds of lines of code. You just scroll through these brief terse interface file. And it's true that IDEs and modern tooling can do much of that for you, but I find that there's a lot of context, like for example version control, or just reading a PDF documentation where you don't really have access to that kind of tooling, and just having everything be explicit is good. Kind of a running theme throughout the language is that it's designed so that you can write code while keeping as little as possible in your working memory, so that it's you don't have to scroll through a huge file of implementation. You just search the interface file to see what's going on.
I've got to say that is quite nice. That is quite nice. Yeah.
I mean, this is much of this from my experience from using OCaml, where it's just so convenient and such a lifesaver, and especially for organization and for being able to like sketch an implementation ahead of time. But yeah, specifically with this API, this kind of like a 2-level API where you have the database API and then the transaction API. And when you start a transaction, the database goes away. It's like hidden inside the transaction object, and you can only get it back by committing or canceling the transaction. So it implicitly only lets you do one transaction at a time. So like this is the basic usage.
Hey. Yeah. That's great.
So it may not be a decidable constraint, in which case the start function would return both the transaction, like a tuple with the transaction and the database. But you may want to have just one database, one transaction at a time. And so the usage is basically this. You open the database, you start the transaction, the database is consumed, you query with the transaction, you put a string, never mind the results because this is
irrelevant.
And you take the new transaction that is the result of query, then you commit the transaction and you get back the database and you close it, completely linear. And if you draw the graph of state transitions, it's somewhat rather complicated, but this is what you can do. And if you were to draw like the graph or like all the permitted transitions in a normal programming language with linear types, it'd just be an ocean of red.
Right.
And of course, in trivial examples like this, it doesn't really matter because you can obviously tell where you're forgetting to close the database, where you're forgetting to deallocate memory, where you're reading from the socket after closing the socket. It's not, the toy examples don't really may not really motivate this well, but the point is like when you're stuffing database handles in data structures and passing them around and everything is very separated in time and space, that's where the bugs happen, and that's where the security vulnerabilities happen, is when things become separated in time and space, and you can't easily like trivially verify the security properties by just reading the code, because the code is just this labyrinthine mess. And what's next? Just a brief note on borrowing. So like Rust lets you borrow linear values, and what that means basically is in Austral, between creating a linear value and destroying it, you can, within a delimited block of code, take a reference to it, either a readable reference or a mutable reference, and it's guaranteed not to escape that particular context that it's in, and not to outlive the thing that it borrows from. And borrowing works. It's essentially stolen lock, stock, and barrel from Rust, but it's pared down a little because Rust is really focused on ergonomics and making code friendly to like C++ programmers. So the Rust's borrow checker actually has, in the trivial cases, it's quite simple to know like how lifetimes work, but in more complicated cases, especially when you're involving things like anonymous function like closures or asynchronous
it becomes
stuff,
a nightmare.
It's actually quite involved.
Yeah.
How the borrow checker works. And there's like lattices and joins and abstract computer science concepts, and I actually checked the source code to do the comparison. It's the borrow checker is 27,000 lines of code, and I think that's twice the size of the Austral compiler, which is a rather unfair comparison because the Austral compiler is written in OCaml. It's a higher level language, so there's inherently less code, but it's a hell of a lot of code, and there's a lot going on. And whereas Austral's linear type system, including borrowing, including the ergonomic features, it's 600 lines of code. At one point, I actually wanted to implement more Rust style ergonomics, and the implementation just grew so complex that I was just getting lost, and I had to like write like a document to myself. Okay, like, so this is the data structures that we're using, and this is step by step. Let's like walk myself through the algorithm, and it was just nightmarish. And I started thinking about these features that are not in Austral, but they may be in the future, and how would I implement this? How do they intersect with borrowing? And I would have to rewrite the entire algorithm and make it even more complicated. So I realized this is naturally worth it, because implementation complexity is also language complexity, because when you're reading code, you're kind of taking on part of the burden of the compiler, right? Like, type systems are simple enough that when you're reading code, you're running the type system in your head, and you're like running the rules in your head. And if you can't do that, then you have the situation with Rust where it's like you are what people say that the learning curve is like fighting with a borrow checker. And that's a very like apt analogy, because you're not expected to learn how it works. You're expected to sort of iteratively work against it and sort of induce a model in your head of how it works. Whereas with Austral, the intention has always been there's a finite set of rules. You learn them once, you apply them everywhere. The trade-off here is a bit less ergonomics, a bit more verbosity, but you can be sure that like there's no hidden language corner. There's no there's little room for like language lawyering or people debating what does this line of code do, this type check. It's quite trivial to run the compiler in your head, and that's why the borrow checker 600 lines of code. It's not because I'm a great programmer or because OCaml is such a wonderful language that it allows you to move mountains with a whisper. It's because it's doing less, and there are trade-offs to doing less. But languages occupy different volumes of language space, and you're allowed to make different trade-offs. Yeah, and just the brief overview of this.
Yes.
I don't want to spend too much time on it because it's a kind of a convenience feature. It's just
still important, though. I quite like it.
Yes. Yeah. Instead of just taking, this is also incorrect. This shouldn't return file. Instead of taking the file and consuming it, you just take a read-only reference to the file in the region. Regions are the equivalent of a Rust lifetime. So instead of writing this, where you just have to continually assign one variable after the other, you just write this, where it's a much simpler code. And you're just like temporarily borrowing this and temporarily borrowing this. And the compiler can very simply say, okay, this reference does not escape the expression because the expression returns nothing. So it's safe, and it begins after the definition of the variable, and it happens before the thing is consumed, so there's nothing to worry about. It's just simple. And finally, what linear types give you is you get safety, because a whole class of security vulnerabilities is now gone. And you don't need a garbage collector. You don't need to hide memory access behind a fig leaf. You can have all the performance and all the customization of low-level memory management with none of the security risks. You get increased. The code is a bit more meaningful, because now types don't just represent memory shapes as in C, and they don't just represent like meaning as in Haskell or Ada or languages that allow you to define very fine-grained types. They also represent protocols. And so essentially, whenever you have a protocol that's like a state machine, you make a type for each state, and the functions that take a value of one state and return another are the valid transitions. And you can implement any kind of like handshake, any kind of like network protocol. You can implement anything that's staged. You use linear types to ensure that there's only one way to write the code, which is by following the correct protocol. And the programmer, whereas in C, like, you have all these functions and you have to read the documentation to know what order you have to call them in. And even if something works, you're not quite guaranteed that it's working correctly. There's a lot of like lore to C interfaces where it's like, is this really how it's done? Am I wasting memory? is there's like, the graybeards can tell you that actually the right way to read from a socket is so and so, but here there's only one way to do it. And of course, because there's only one pointer to each value, you get concurrency for free. You don't have to use locks or mutexes or semaphores or any sophisticated concurrency mechanisms. You just, when you want to do something multi-threaded, you have your threads and you have channels connecting your threads, and you pass a linear value from one thread to another through a channel, and it gets consumed by sending it, and then it gets picked up by reading the channel in the other thread. And the
okay, so that wouldn't consume the channel. No, that would
no, I mean, you can
consume
have
the linear type that's traveling in the channel.
I actually have an API for like linear channels. It's kind of cute, but I haven't like finished it yet. But it's like channels would also probably be represented as linear types because they do have a life cycle. They have to be open and they have to be closed.
Yeah, but you would read values from it, so you could read multiple values from it, right? But that doesn't mean that you're gonna close it, right?
Well, it depends
like a
on
socket.
You can have a channel can have room for one value, or it can be a queue.
Right.
There's different
buffer.
inter-thread. Yeah, there's different like inter-thread communication mechanisms. Like the if it has a single value, the function that puts another value in the input.
Oh, then it's a one time. You can kill it then.
Well, I mean, like if suppose you have a channel that's like it's one way and it has room for one value. So the function that puts a value in it, it either returns nothing, or it returns the object that you try to put in if the thing is full. Like you have to design the API so that it's not like silently discarding the values that you put in. I mean, anything that involves raw like foreign function interface type stuff, like the file system API, like the memory API, like sockets, like channels, you have to build a linear interface over a fundamentally unrestricted foreign API. So you have to, at the edges, at the foreign function interface level, you do have to take care that things are implemented correctly and that things don't violate the linearity rules. Because when you're calling a foreign C function, C doesn't know linear types. You need to use raw unsafe pointers. You need to use that kind of thing. So the idea is that there's a trust boundary at modules that provide a linear interface and like an unclean, dirty, unsafe implementation. Yeah, and for channels, if you want to pass a linear value, yeah, the channel has to be like empty and available for putting things on it. I can also sketch, I'm going to write this down, sketch a recursive function and also sketch like a linear channel API.
Brilliant.
To show how this would work. I haven't had either the time or the necessity to implement like inter-thread communication stuff, but you can do it safely. It's actually quite simple. You just the linearity guarantees are easy to preserve in the interface. Essentially, this is the same thing that Rust does. Rust is kind of similar. It's more like affine types. The difference with Rust is that Rust has a much more sophisticated ownership tracking scheme because the focus on Rust has always been on like programmer happiness and ergonomics, and that involves doing a lot of work on the compiler on the programmer's behalf. And yeah, but the basic idea is the same as Rust. There's only one mutator for each value. So when you surrender a value from one thread to another, the ownership, the linearity guarantees are preserved, and there's only one copy of it. Right. Yeah, and the final thing that linear types give you is capability-based security, where I think I just wrote briefly about this. Yeah, the motivation for this is that we have all these software packages, and code in every programming language essentially is uniformly permissioned, in the sense that within the address space, there's no way to say that a particular piece of code can do X or Y or Z, but not other things. You can have, right, so when you pull in a left path dependency, you don't know if that actually has malware that is going to hoover up your disk and send it to a remote server somewhere. And you have these supply chain vulnerabilities that are quite new. Like if you read the software engineering literature from the 1980s, everything's about software reuse and how do we make software more reusable and allow people to share code. Well, it turns out that we have the opposite problem, where we have millions of packages and everything's vulnerable to supply chain attacks because there's no way to specify any of the security properties. All of the security properties really work without the address space. Like on Linux, you can restrict the capabilities of an executable. On OpenBSD, you have something called pledge, which basically says, I won't use the console or the network or whatever, and the program terminates if you try to do any of those things. But the basic idea of capability-based security is you are like understyle permissions to code, and this limits the this lets you prioritize what you want to audit. If a left path function doesn't take any like capabilities, it's just not doing anything other than maybe allocating memory. But if a left path function takes a memory access capability, that's like a network access capability, that's suspicious and that should be audited. And of course, the boundary of this is the foreign function interface, but you can't use the foreign function interface everywhere. You have to use it in modules that are marked as unsafe. So the whole point of this is just to sort of like make code auditing easier. Like the only code that you have to audit is like unsafe modules that may use the foreign function interface and unsafe interfaces and things that seem to take overpowered capabilities. But I haven't explained what a capability is. And what it is like a non-duplicable, unforgeable token or permission to do something, right? You can surrender it, you can destroy it, you can give it up to somebody else. You cannot duplicate it, and you cannot acquire it out of thin air. You have to acquire it from some higher, more powerful capability. And yeah.
Oh, I know. I'm letting you explain, and then I might have some questions.
Yeah, and basically capabilities in Austral are implemented as linear types because linear types are destroyed by being consumed. They're surrendered by passing them to a function or a data structure that captures them. They're not duplicable since linear types cannot be copied. And yeah, the fourth restriction basically involves this, which is at the entry point of an Austral program, you have something called the root capability. And this is a function that this is a value that's a linear value, and so you have to dispose of it before you close the program. And the root capability cannot be created by the programmer. It can only be created by the runtime, let's say. It appears fully formed when the program starts. You can't create it out of thin air. And this is the root of the capability hierarchy. This is like a simple example, like using a capability secure file system API, where you have a file object which is linear, a file system capability object which is linear, and this function getFS, it takes a reference to the root capability, which essentially takes proof that the client has possession of the root capability, and returns a file system capability. And then OpenFile takes a reference to file system capability and a path. It essentially takes proof that the client has the file system capability, and it returns a file. And write string just works as usual, takes a reference to the file, string. This is actually a mistake. I prepared these slides like an hour ago, and this should just return none, because it shouldn't return a file because it's not taking the file object. It's just taking a reference to it.
Yeah.
And then you have this function to release the file system capability, which consumes it and does nothing, and close file, which closes the file. And the way you use this is like this. You have the program entry point, you have the root capability, you acquire a file system capability, you acquire a file, then you write a string, you call getFS by passing a reference to the root capability, and you acquire the file object by passing a reference to the file system capability. And then when you have the file, you can do whatever you want with it, write to it, close it. And finally, because FS is a linear type, you have to consume it by releasing it. And then you can do whatever else you want. And eventually you release the root capability, and you return exit success. So the basic idea here is that you, and this is a very simple, minute example, but the idea is that you can be arbitrarily granular, and you can have a whole hierarchy of capabilities where you have the root capability, which is the ability to do anything, but you could have a file system capability, a file system for just a directory, or for just a file, or for just a file for like read-only access, or for write-only access. You can have a network capability for using the network, and it could be limited to just sending things, or just receiving, or sending and receiving to a specific host. You can limit access to the clock, because compromised packages can use the clock to do timing attacks. You can be arbitrarily granular, and you can lock down everything about how the how your APIs work.
I just love this. I just absolutely love this. If you can go back to one slide, I think this is absolutely fantastic. So, for example, like under getFS, you could say, okay, I'm only going to limit you to, for example, etc/etc/whatever.
Yes.
And then the program executing this just cannot see anything other than what it has given permission to.
I mean, like linear types are capabilities. Like if you imagine the file object is a capability. If I have a file object, I can write to it and I can just dispose of it. But if I don't have a file object, I can't do that.
No, this is absolutely fantastic, and I really like the way that it's very much a hierarchical thing, and the runtime actually generates this root capability, and then from there it's up to you to sort of like pass it out. So if you were to publish like for example a library that's with a set of methods that upstream would actually use, then you would expect them to pass in a certain capability, and it's up to the host program or the program calling the libraries to actually say, well, I don't necessarily trust you.
Yes,
you're a left hand and you could do some sort of dodgy shit. So I'm only going to give you a little bit of a quarantine, a cordon sanitaire area to operate in. And
I mean, obviously every language has a escape hatch, and in this case, it's a function interface, and that's where all guarantees are over. But this is true for every language, and so it's not about absolute guarantees. It's about, okay, how much do I have to audit? Okay, so this is an unsafe module. It can use the foreign API. I'm going to stop sharing now because it's the where is this?
We're at the end now.
It's already this is done.
Okay.
And so it's like, what was he saying? Right. It's about minimizing how much you have to audit, because ultimately you do kind of have to audit your code, which nobody does, but everyone says that you should whenever there's a like a horrible a horrible hack and everyone loses their social security numbers. People say, well, they should have audited their 500 trillion lines of node modules dependencies. Well, I mean, this sort of, that's just not realistic. And building an app without dependencies is also just not realistic in a business sense. So you have to kind of find the efficient frontier there. And the solution is simply just put some permissions on code. And I really love linear types because they're I should just wear a shirt that has like Philip Wadlow's paper called "Linear Types Can Change the World," because they're kind of like a secret sauce where they solve a lot of problems, and there's many ways to implement it. And I think the Austral approach is really quite simple. You have to absorb a couple of new concepts like all this stuff about the type universes and the universe split in two, and these things that are unusual but not terribly complicated, except that maybe the terminology is new. But the benefit you get is tremendous, because you get clearer, more strict, more locked down code, and you get all these security vulnerabilities that go away.
Well,
and I should
also,
note,
there are other things. You get a much tighter implementation, so now you can target embedded sort of environments, right?
Yeah.
This is quite nice. You were going to say you should highlight.
Yeah, I should note, I just noticed while I was going through it, of course, I noticed while reviewing, there's a few syntax errors in the slides. I will post the corrected slides on like Twitter or something. But yeah, don't run the code straight from the slides. just a brief note. I forgot a few return types.
Oh, that happens. That happens. Now, like in some one thing I do appreciate, for example, with a fellow by the name of Jonathan Blow, who's creating a programming language called Jai. I met him in Hong Kong, and yeah, he came through. He was out in Asia for a while. He had a number of conferences that he was attending, and somebody mentioned, I think it was on Twitter, that Jonathan Blow was in town, and who wants to come. And I went through and I met this fellow. John's pretty goddamn hardcore. I really like that fellow. But one thing that he's done is that he's actually created an actual example, or it's going to be turning into a real world, like an actual product that he's creating on top of Jai. It's implemented in Jai, which is a Sokoban type game. Do you have any sort of application that sort of like, kicks the tires of Austral as you're going? So the actual program informs the implementation and the language design. Language design can benefit the application that you're creating.
So far, I've avoided, like, for example, rewriting the compiler in Austral, because the problem is that biases the design towards making a programming language that's great for writing compilers as opposed to building.
Yeah, no, it doesn't necessarily have to be the compiler. It doesn't have to be bootstrapped.
I mean, I mostly focus on like building examples and building test cases, and I'm working on the standard library at present. The language is effectively done. There's really, I mean, of course, nothing is done, and things are only ever asymptotically done, and that's very frustrating. But yeah, I'm drafting, like, the next release is going to be like core language done, and there's only a couple of language features that I have to implement. It's really like just like this minor subtlety, like generic type parameters in type class methods, which that doesn't have to mean anything. Yeah, just a minor corner that's left unsanded, and afterwards the language is like ready for use, and not necessarily the wisest thing to use in production at an early stage, but you can experiment with it and build real things with it. It's at least as safe as C, because the bootstrapping compiler just throws out a bunch of C code. So because it was simpler than, dealing with LLVMs fortnightly breaking changes and building 500 gigabytes of source code. Leave me alone. I'm just gonna use GCC, whatever. Yeah, I have a few applications that I've had on the back burner that I've when I finish Austral, this is gonna I'm gonna write them in Austral, and it's like, okay, how long has this been going on? I think I'd like to write the build system and package manager in Austral. The standard library that I'm working on now, obviously it's gonna be written in Austral. Applications, I've long had a project to write like a LaTeX replacement, like a document preparation system, because for some reason this is like the thing that I'm cursed to do for all eternity, is to write document preparation systems and personal wikis. I've done this like 17 times, and yeah, I have this mostly formed idea in my mind of what I want for from a LaTeX replacement, and I think I could write it in Austral. it's mainly just about, because LaTeX is just this strange 70s thing that I mean, it's just so strange that it hasn't been replaced yet. So finicky and weird.
Yeah, and indeed. So yeah, okay. So what did you find that capabilities just sort of emerged out of the design of choosing linear types, or was that an active design goal that you were seeking? Because it feels like something that's sort of just like, oh, and here we have this now. Do you see what I mean?
Yeah, this is one of those instances where I wish I'd kept better documentation, like a lab notebook or like what my thoughts were at the time. But it does emerge quite naturally when you think about it. I think, goodness, I'm sure I can find a bibliography talking about the connection between linear types and capabilities. I think there's a Microsoft research paper for like the Bolt programming language where they talk about like type states, which was this thing they made up to like handle like oh yes, now I remember. I think there's a paper called aside from the type state program, there's a paper called Enforcing Low-Level Protocols. Enforcing high-level protocols in low-level software. And I think that talks about like a linear-ish type system for doing capability-based security. I'm sure I can find some paper that incepted the idea in my head, but it really does fall quite naturally out of the design. Where, yeah, I mean, you have these rules, and the linear types are themselves capabilities. Because if you have a linear value, you have permission to destroy it, to do whatever you want with it, and from that you quite naturally get the notion of we can represent permissions, and because there's actually kind of a spectrum. Like a file object is a file pointer, but it's also a capability to do something with that file. The root capability is like an empty type. It doesn't have any values because it doesn't represent anything except the semantic concept of being a permission slip. It exists mostly exclusively at the level of the types, and ideally the compiler would just not materialize it because it contains no data. So there's a spectrum where at one end you have things that are more pure capabilities. They carry no information. They're just permission slips. And at the other end, you have things that are more like linear values that have like a file object that has that contains an actual pointer to a file that you get from the C standard library, or a database socket that inside of it actually contains an actual pointer to the database socket. But they're all capabilities. I think the pure capabilities are the ones that exist purely for like clerical purposes, that don't have values, that don't hide some implementation detail inside of them, that are just about permissioning code and determining what piece of code can do what.
All right. Within the language that I'm trying to implement, it's called SEO.
Sorry, what's it called?
SEO. SIO. Secure input output. Rather lame. I just wanted the 3 letters.
And some good.
and
I like acronyms.
Yes.
A lot of people find them, stodgy.
Now, one thing I'm going for is the Erlang style lightweight language processes, and because I just love the supervisor nature of Erlang. Erlang OTP has a series of supervisors, and the idea is that if there is an error that occurs within myself, I'm not going to do a self-operation, as is the case of that fellow there down in Antarctica, the only medical doctor down in Antarctica, and he had an appendicitis, so the only one who could perform the operation was himself. He told his colleagues, like, hold the mirror in this position, and he cut his gut open and removed the appendix himself, and so then somebody else might have sewn himself up. So the idea is that you always want to have somebody else other than yourself to fix you up. In other words,
I think that makes sense with regards to what we know about like computer security at present.
Yes.
recovery mechanisms are handholds for attackers to use, and it is, I think, almost overwhelmingly the case that whenever you have whenever you find yourself in an inconsistent or suspicious state, just crash the process or the address space as a whole, preferably. And that's how Austral does error handling. It's actually very Spartan. It's sort of like Rust's panics, just crash the whole thing.
So this is exactly the right mentality, in my opinion. So when I
yes,
saw
but
this,
I think I think Austral is a bit more perverse in that it just crashes the entire address space, whereas with Erlang you have the lightweight processes.
right?
You just crash the process, and Rust works the same way. You have tasks. I think it's the terminology, and panicking crashes the current task, but not everything else. I think I'm pretty sure that's how it works. But yeah, go on.
So this is exactly the idea, is that when one has a virtual machine that supports lightweight language processes, and you re-implement a supervisor type hierarchy, a supervisor does one and only one thing, and that's to monitor its workers, you see. So the workers would do the processes, and then the functioning. And then should a failure or an error happen within one of those things, just abort the address space, just kill that process. And then the supervisor might have a set of rules, and it's programmed to do certain things. For example, maybe the supervisor says, okay, one of them crashed, so I'm going to execute all of them and then start up the entire set of workers. Or it might just restart that single worker. So in this way, you actually have an error recovery mechanism, which actually just basically it returns back to a deterministic result. You know, you move away from non-determinism, and then by doing this execution sort of style, you can bring it back into a deterministic state. Because and the reason why I say that is because I'm implementing a data flow programming language, concurrent data flow, which means that it doesn't matter how many threads or things that you throw at it, it will always be deterministic on the outside. So anyway, so I mean, that's just a nice side effect that sort of comes from or what you've got in Austral, how you handle the errors. But in your situation, you just abort the entire operating system process. You just kill it all.
There's a gradation. There's a section in the rationale of the language that explains the reasoning behind the error handling mechanism more thoroughly. The basic idea is that you have this categorization of errors, and you have things like abstract machine violations and invariant violations, like an assertion that's false, or Stack Overflow or things like that, and those crash the program. And then you have things that are more pervasive, like memory allocation failure, or things that are not really quite failures, but just expected circumstances. Like if you open a file and the file doesn't exist, that's not cause to throw an exception. It's you just return a value. The file system APIs that I showed in the example, they don't have any error handling stuff because obviously it's introductory material. It's it would take the focus away from the introduction. But yeah, the basic idea is that as in Rust, as in Haskell, as in every functional programming language, failure conditions are handled by values, by just using values. And things that are really quite severe or indicative of a computer security problem lead to terminating the entire address space. Where was I going with this? So yeah, there's actually a rather lengthy section about this in the rationale for the language, about how I chose the error handling thing. The reason Austral doesn't have like traditional exception handling is, first, it's not compatible with linear types, and there's a rather lengthy proof of why that's the case. And this is actually why Rust works the way that it does. A lot of Rust's design decisions, like how destructors work, The fact that types can be discarded silently, not have to be explicitly consumed, is because Rust wants to have like traditional C++ Java style exception handling, where you throw an exception and it unwinds the stack and calls the destructors for you. You can't really do that with linear types. You can do that with Rust's ownership tracking mechanism. The problem with exception handling, and the reason I rejected it, is that it's hugely complex. I mean, a rule I have for Austral, I call it an anti-feature because it's one of the features that it doesn't have, is that there's no surprise control flow, and there's no like hidden function calls or anything like that. If it's not on the page, it is not happening. And yeah, I mean, people have said a lot about exception handling, about performance claims, often hard to substantiate. There's pros and cons, but I just have like there's a section on the rationale that's just like my 95 thesis against exception handling, and it bloats the code. It's implicit control flow. You can't reason about it. The compiler struggles to optimize code because every function call is like a landmine. It will go off or maybe not. Lots and lots of problems, which I won't necessarily go over. But yeah,
I completely agree with you, and as a result, like after, like I'm totally in your side of the court on this, and when you join this with lightweight language processors, which have the attitude of, well, fuck it, just die. It works so well, and it removes so much complexity from things.
Yeah. Because when you do actually handle errors, when you do actually renounce exception handling and just decide to handle errors as values, that's a nice thing to say in theory. The actual practice of it is not great. Of course, people complain about Go, where the median line of Go code is if, error, nil, something like that. Just there's a lot of error handling. The same is true with Rust, to a lesser extent, and the same is true to a probably greater extent with Austral, where there's, if you want to do things correctly, it's very verbose. So for like prototyping code, you might just say, okay, abort here, and I'll come back to this and I clean it up and do like proper error handling later. I know definitely that in the implementation of Austral, which is written in OCaml, some of the code handles errors as values, but much of it just throws an exception and just gets out of the way because that's just simpler. And it is, I mean, just doing it right, handling errors as values is, I think SIG, which is a new language, has some ergonomic tools for this. It has some convenience features for doing this, like with less horror. But it's just such a nightmare. And when you can just destroy the process and clean everything up automatically and just restart the process, that's such a boon, because you can, as with exception handling, you can just focus on the happy path and ignore the error handling until the program crashes. Now, the problem with lightweight processes and just crashing just the process is that it's not really compatible with linear types, because the compiler doesn't have a special knowledge about what is a destructor.
Oh, shit.
Yeah. So like in Rust, there's you have the drop method of drop trait, and that's the destructor interface for all types. So the compiler knows what the destructor is, and it knows it inserts destructor calls implicitly, both for the happy path when something goes out of scope, and also it inserts the destructor calls in the exception handling case, where the code that unwinds the stack and calls the destructors is generated by the compiler. With linear types, because there's no implicit function calls, there's no implicit control flow, there's none of that, the compiler doesn't generate code for you, which means you can't clean up automatically in an unplanned abort, because there's really nothing to do. And I thought about this for quite some time. There's really no way to preserve soundness, which means, and the reason why Austral crashes the entire process rather than the thread is that because there are no destructors, the destructors do not get called. Sockets and files do not get closed. So if you try to just crash the task and restart it, you would leak memory, and you would leak file handles, and you would leak network sockets, and eventually you would have a denial of service attack. So basically, Austral relies on for bugs and things like that. Austral just relies on using the operating system as a garbage collector, basically. Crash the program and let the operating system recover the memory and the file sockets and the locks and things like that. Which is why most errors have to be handled as values within the code, as opposed to just crashing the program. And crashing the program really is restricted to things like invariant violations that are bugs in the code, not errors. Abstract machine violations like the stack overflows, and things that are like probable security vulnerabilities that if you have like an integer overflow, that could be an attack, just kill the whole thing.
So I might be able to get away with this because I'm targeting in an embedded environment. I deliberately don't want to have an operating system. Some of the logic behind this is that I'd like to have a programming language which has authority to spend my Bitcoin hot wallet. So, which is a little bit nerve-wracking, right? So,
yes.
So the attitude of security is quite, I have to be pretty strong about this. In other words, only a single process, a lightweight language process, will have authority to write transactions and then submit them into the Bitcoin network. But then also at the same time, because of capabilities, it would actually grant capabilities to authorize processes to make requests and to make requests for those transactions to happen. But at no time will any other process, process, be able to see the private key, for example. So now where was I going with this? We were talking about we were talking about errors. Oh yes. So and also I want to avoid the concept of file systems entirely. I don't want access to any file system, because I've created a new networking protocol, which is an information centric protocol. It's a new fancy stuff. It's not like a IP based. Basically, it's a replacement of IP. And you can actually request information by name. So, for example, your public key, and then slash. It might be the slideshow, for example, a hierarchical naming slideshow, and then eventually your virtual machine sitting on your system over there will get a request, and then it'll say, oh yes, okay, it's coming from Stewart Mackenzie. I'm happy to send it back. So then it'll encrypt it using my public key and your private key, and then I'll take it back because I have your public key. I'll be able to decrypt it and then get the information from there. So this adds a more levels of security, in the sense that everything that's beyond the lightweight language process boundary gets encrypted. So so this means that and every process is addressable via the public key. So this sort of like adds an interesting level of information, in the sense that I'm hoping that all of the lower level stuff, for example, access to networking sockets, etc., is all at virtual machine level. Could be, say, like the operating system level. And then the lightweight language processes can only communicate by sending these bits of information in encrypted form using this networking protocol. So as a result, I think I might be able to get away with but then one asks, like, at that point, does one actually have any sort of need for a linear type within the actual process itself?
I don't know. I mean, if you have like if the language is sort of like a pure function that takes its values and just returns some simple value like a string or some such, it you may not need that. It depends. I think domain specific languages have generally lighter restrictions, whereas Austral is meant as a general purpose language, which is kind of, I suppose, a DSL for algorithms in general. So yeah, it's meant to be able to handle like a wide range of things. I think it depends on to what extent you want this to be a DSL. I think, like, for example, Bitcoin has Bitcoin script, which I think is like this very small stack-based virtual machine with like 6 opcodes or something like that. It's very limited. So depending on the amount of power you need, you might be able to get away with like a virtual machine and a very small language-like thing or code, like a fourth or something.
Yeah, no, I have thought about that, but I prefer it to be a general purpose language kind of thing, because I'd like to do all sorts of like maybe calculations or decisions based on other people's information, because everything that you create will be signed by you. So I trust you that maybe you for example are giving me the right weather of in certain parts of, maybe you're in Australia, and because maybe I trust you, so like I trust your certificate, your public keys, and therefore I might make decisions based on that. So yes, there's an element of trust and in these sorts of systems, but and finally maybe depending on a number of sources of input, because it's basically I'm implementing trusted computing at this point. I might make a decision which results in, for example, spending Bitcoin. But
yeah,
but the Bitcoin spending is just it's just basically it's like a requirement that I'm imposing on myself to design a secure system. Do you see what I mean?
yeah.
It's like it's not necessarily like my primary goal of using it. It's just like, okay, let's have a system which is like a secure input output. Okay, I put my money where my mouth is, right? Yeah, something like this.
I have 2 ideas here. The
Oh,
first, I think, is varying levels of practical, but if you have a sub-Turing language, a language that is
a total
general
language.
purpose, yeah, and not Turing complete, you can prove a lot more. Of course, that somewhat takes the general purpose out of it, but you can. You don't. People have written large programs in total languages. You don't need Turing completeness everywhere, and I guess especially for compilers, might not even need Turing completeness in a lot of the passes. The second is there's a trade-off between theorem, between software verification and the complexity, both of the implementation and the semantics of the language being proven, because you have type systems and then you have fancier type systems like Haskell or linear types.
Diminishing returns.
Well, and not necessarily. I guess in the sense that you're taking off more of the vulnerabilities, but if you want total assurance, you need something like automated theorem proving, or like a proof assistant or an SMT solver, or Ada has a subset. There's a subset of Ada called Spark, and it's a name that's very overloaded, and there's like 50 million software projects called Spark. But Spark is basically just a subset of Ada that is translated to the Y3 theorem prover to make proofs about like totality and correctness. And it's a very old project, and it's had a lot of work done on it. And you can actually prove quite sophisticated things. You can prove the correctness of sorting algorithms. You can prove all sorts of things. You can prove it's used, in like defense, aerospace type stuff for safety critical things, things that human lives depend on, which I would not use Austral for, just to say I would not use C or C++ or Rust. When human lives are on the line, there's genuinely and it's arguable when you cross this point, there's a genuine professional need to use much more sophisticated tools, and that involves theorem proving and guarantees of formal guarantees of correctness. And Spark is nice, but it is a subset. And I mean, it is a subset. It's very, very Spartan what you can do. And it's only very recently, because Ada, even though it's a low-level language, it has some nice properties. It has like stack allocated arrays, which unlike C are actually safe. Stack allocated arrays with like a statically unknown size. So that lets you avoid using pointers for a lot of things, and like embedded devices can use fixed size stack allocated arrays where otherwise a C program would have to allocate memory. So Ada, as a consequence of that, Spark lets you put quite a bit of code, and recently pointers used to be banned, and I think recently they're like backporting like an ownership tracking scheme from Rust, so that you can prove things or code using pointers. But that's a rather recent change, I think. I would say that Ada is probably like the Spark Ada is probably the most like sophisticated, or like let's say the most practical software verification thing for like real things, like real medical devices and things like that. But there's other options for C and other languages. This really isn't something that has an easy answer, because verification is such a complex topic, and it deals with mathematical logic and proof, automated theorem proving, and what's a proof, and verifying the correctness of the proof itself, and there's all sorts of difficulties here. So being able to use your Bitcoin hardware wallet is
hot wallet, not hardware wallet. Hot wallet.
Sorry. I misunderstood. Hot wallet, right? The one that's connected to the internet.
Yes, that's right.
Yeah, that's rather a heavy requirement, because it's not quite a pacemaker, but no. It is a lot, and it is hard. You have all these contract languages for like blockchain stuff that I haven't really kept up on.
No, I can't be bothered with all of that stuff. Just keep it simple. So the idea is that those contract languages, those sort of smart contract language level stuff, I think it's a bad direction, because they all want to consume the world. Do you see what I mean? Like, how the hell are you going to? You run a pizza shop. You want to put every single transaction of like some pizza that you've made through, or whatever conditional contracts. It's you can't do that. You can't take all the information of the world and stick it on a blockchain. It's just a non-starter. So the idea now is that you just have the consensus layer on the Bitcoin level, which is also acts as like a time global timing sort of mechanism, marches the step by step. And then you just have a distributed programming language. And the idea now is to use Church Rossa, which is a sort of a subset of functional programming, which allows you to have these like a functional programming which can operate and execute over distributed nodes, but does not require consensus. It's not. Yes, it converges. It eventually converges, but you can still make decisions about things, and like once it's converged, because everything's data flow. Every variable is a data flow variable. So either you can instantiate, for example, I is a U64. But it's not bound, so it's unbound, and you might be able to send this variable to somewhere else, and then later on it gets bound, and then once it's bound, it's monotonic in the sense that it forever remains bound. So I'm also thinking maybe so it forever remains bound, and you can basically throw a whole bunch of concurrency primitives at this, spin up a number of threads, but because of the immutability of every single variable, it will converge to that value and remain deterministic. So once you have this direction of determinism, and you introduce the Church Rossa sort of like theorem, you can now start to do distributed computation across number of nodes. Of course, you need to introduce things like capabilities and like encryption, because you're on the open internet. It's not like Erlang, which is a high performance cluster. You try doing Erlang over the open internet. It's really not a fun thing. It's not fun. It's fucking hell.
The internet is not a great data center.
No.
I mean, I don't know much about distributed programming, actually.
Yeah.
Right.
It's a bit of a different kettle of fish, but yeah, the primary thing is the distributed programming, and then the idea is that like because now every single process is now addressable by public key. In essence, one could implement something like, for example, like a Lightning network, but you don't have any IP addresses in there, man. It's just like I send information to your public key. I send a transaction to your public key. End of story. And even if like, for example, in a noded networks, the virtual machine will talk to the IP address of another virtual machine, but on a higher level, on the information level, addressability is not via IP address, it's via public key. So if I send information to your public key and this particular IP address channel breaks down or something, then it'll just reroute through another pathway over another set of IP addresses. Anyway, this is addressing a different level.
This is for the protocol that you're working on.
Yeah, I've already implemented it.
Yeah,
and it's called Copernica, but I think I'm going to re-implement it. But this time I'm going to be targeting an embedded environment, which poses another set of challenges.
Yes, especially with like memory and not having an operating system. I mean,
yes.
This is a combination of two hard problems, which is distributed computing and embedded computing, and actually a third problem, which is verified or trusted computing, and how you ensure that the program is doing what the formal specification says. So this is rather ambitious, ambitious conjunction of open problems in computer science to tackle.
I know, but I got to occupy my time, man. I got to occupy my time.
I know you have the things. You have to get the projects out of your system.
Yes. Otherwise, I'd just be driven mad here. Like it's just got to come out. It's some sort of like, some people like to dance, right? I have to do this.
Yes, I know the feeling.
Yeah. I suppose we can move away from programming languages and whatnot. What other sort of like where you're in Australia now? Is that right?
Yes.
And originally you're born and raised in Italy?
Uruguay, actually.
Uruguay. Interesting. Okay. And then what brought you to Australia?
Yeah, I always wanted to leave Uruguay, and I felt like Australia was a good choice. It's an Anglosphere country where people speak English, and there's good weather and things like that. And I just got a work visa and I moved here just late 2019.
Don't you miss home? Don't you miss Uruguay?
I miss my family.
Okay.
I miss a few friends. Not terribly. Quite frankly, it's much better here.
Is that so? Well, okay. Things are more stable. I mean, but
I mean, it's I would say it's the opposite of the death of 1,000 cuts. It's everything's better in subtly different ways, in 1,000 little subtly different ways.
Okay. Yeah, no. My wife would love for us to move to like Melbourne. We're based in Hong Kong at the moment, and Melbourne is number one on her list. So she keeps like, come on, let's go over to Melbourne. No.
Melbourne is nice. It's arguably better than Sydney in some ways. Sydney is a really beautiful city.
Yeah.
Arguably, Melbourne has better nightlife. Gloomier weather. Should have a Shinkansen train network because it's a very sprawly. Just don't live too far. But yeah, Melbourne's beautiful. Go to Melbourne. Visit Melbourne at least.
Yeah, we've been there a number of times already. Yeah, no, taxes in Australia are a bit high. I kind of like the tax of Hong Kong. It's good.
I
15.
don't have too many terribly. I don't have too many terrible complaints about the taxes here, the economic situation.
Yeah.
Things are fine. Things are good.
Well, fine. No, fine. Well then, is there anything else you want to sort of like raise and talk about? Maybe technical, non-technical, any sort of like something else that you're working on that you want to point people to, or
go check out the language, open the issues tab, and perhaps if you know OCaml, contributions are appreciated. I have been horribly procrastinating on writing like the introductory post where it's like the official,
welcome to the world.
Come look at the thing post, where I would outline, beyond just contributions, welcome, just like what people can work on. And yeah, I think like the language is like developing at a good pace. The compiler is essentially finished. It's not the smartest compiler in the world, but it implements the language faithfully. I'm building like a simple standard library. Eventually, there's going to be like a build system / package manager. I really appreciate it as like a learning opportunity, because how often do you get to like design a standard library for a language? And you get to learn all the data structures and all the file system APIs and things like that. And I have a small number of other technical projects and things that interest me, and like non-technical projects. Follow me on Twitter.
Yeah, I'll put that in the description of the video.
Good.
But Fernando, I really appreciate your time. Thanks so much for
having me.
Yeah, thank you for writing such inspirational work, both the code as well as the prose, and giving this overview of linear types. I think you've sold me on it, and I'm going to definitely try to work that into my language, and I might even list Austral as an influence of my programming language. So there you go. I mean, it's barely out of the gates, and it's already influencing other languages.
Well, thank you. At least I can say that I influenced one person. Like Dale Carnegie suggests.
Well, thanks so much, mate.
Thank you for having me. And I'm happy to talk in the future if you like have like language design questions or want a language theory sounding board for like future ideas. Because I've spent an excessive amount of time thinking about like the trade-offs and the programming language implementation. Yeah, I'm ready to finalize this and move on to like actually using the language instead of just building all these languages.
Yeah, great. I appreciate that. That gesture is it's very welcome. I might take you up on that, actually. Good. Thanks, mate. Okay.
Thank you.
All the best. Let me stop the recording now.